correlation between the quantum flux and excess power. When the deuterium gas enters a palladium tube, there will be a flux through the thin wall into the vacuum chamber. If this flux is caused by classical diffusion, that is two-body collisional diffusion, it should drop with the temperature T monotonically. There should be no peaks in flux. However, when the temperature drops from 180 degrees to 80 degrees C, the blue line shows many peaks. These peaks means there must be quantum diffusion flux.
We don't see the graphs.
That is 36 years ago, we learned excess heat. A few years later, we learned that this excess heat is correlated with a deuterium flux. Now we know there are two kinds of fluxes, the quantum flux and the classical flux. The classical flux is caused by two-body collisional diffusion process. Quantum flux is caused by a wave interacting with many bodies in lattice. We call it multiple scattering. This multiple scattering makes correlation between the quantum flux and quantum hydrogen energy. This understanding is based on our teamwork at Tsinghua University. Many thanks to our friends for their assistance. Let's start from this correlation. Correlation between the quantum flux and excess power. When the deuterium gas enter a palladium tube, there will be a flux through the thin wall into the vacuum chamber. If this flux is caused by classical diffusion, that is two-body collisional diffusion, it should drop with the temperature T monotonically. There should be no peaks in flux. However, when the temperature drops from 180 degrees to 80 degrees C, the blue line shows many peaks. These peaks means there must be quantum diffusion flux involved. That is a wave scattering on many bodies in lattice. When we put this vacuum chamber inside
Can you continue?
A microcalorimetry, its precision is 1 microwatt. However, the red line shows a peak of 2 milliwatts, and the peak is correlated with the blue line. That's a correlation between the quantum flux and excess power. How a wave scattering on many bodies in lattice may cause this correlation? Multiple scattering makes correlation between the quantum flux and excess power, plus coherent jump. 2 years ago, we talked about two-body wave scattering. In the current field, the solution of the wave equation is a linear combination of the black one and the red one. The coefficient of this linear combination depends on the phase shift delta. When the incoming wave refracted by the nuclear surface, there will be a phase shift delta. Usually it's very small, so the black one will dominate and the wave function will be peaked outside the Coulomb barrier region. That Coulomb barrier pushes the charged particle away from each other. In the case of resonance, the boundary condition at the nuclear surface will pick up the red one only. The black one disappears. Then the wave function will be peaked at the nuclear surface. This will greatly enhance the overlapping between the initial wave function and the final wave function. So the resonance will increase the quantum transition probability. However, it's not large enough. Even if in the case of many-body resonant transition, if they are not coherent, it's still not large enough. When all the initial state jump to the final state together coherently, then it will be proportional to n squared. Is this possible? Yes. In two-body wave scattering, we consider the boundary condition at the nuclear surface. Now, in the solid, we should consider the change of the boundary condition here. In the solid, multiple scattering happen. The incoming red wave excites the red one. It will emit the blue one. The blue one will scatter back. The blue scattered wave will interfere with the red primary incoming wave. There will be some cancellation. In certain conditions, this cancellation makes the black one disappear. So the boundary condition here may make the wave function peak at the nuclear surface as well. Moreover, this boundary condition can make the transmission peak as well. 50 years ago, low-energy electron diffraction people used the electron beam injection. From the refracted peaks, they may figure out the crystal lattice parameters. Now, we know the crystal lattice. Using the same method, we may figure out the condition for the transmission peak. Indeed, the condition for transmission peak, the quantum flux peak, is same as the wave function peaked at the nuclear surface. That is the excess power peak. So these two peaks are correlated. Moreover, all these scatterers are excited by the same incoming wave, just like a symphony orchestra under a single conductor. They will jump together coherently. This coherent jump will greatly enhance the excess power. Are there any experimental hints for this wave function peaked at the nuclear surface? And for this coherency? Yes. Hint 1. When the wave function peaked at the nuclear surface, there will be a Boltzmann factor. In the two-step nuclear resonance model, if there is no resonance, the wave function peaked outside the Coulomb barrier region. At the nuclear surface, the wave function is much smaller than the wave function there. So when we integrate over the Maxwellian distribution, we obtain this gamma factor. It's hot fusion. In the case of resonance, the wave function peaked at the nuclear surface. When we integrate over the Maxwellian distribution, we obtain this Boltzmann factor. That's cold fusion. In our experiment, we have the first three peak for the excess power and their temperature. We can put the logarithm of the excess power here versus 1 over T Kelvin. We obtain this straight line. It's Boltzmann factor. That is encouraging. Hint 2 is for coherency. Carabot obtained these X-ray diffraction spots from his cathode in gas discharge experiment. It's a collimated beamlet diffraction pattern. It's very similar to the electron beam diffraction pattern. It means the X-ray is from a coherent source. Now, how can we increase the number in coherence? From low-energy electron diffraction theory, we may see face-centered cubic lattice is best to increase the N. This lattice has three kinds of surface, and 100 surface is best to increase this number. Dr. Violante and Makubri showed two samples, palladium samples, with same metallurgical treatment. This one is 100 surface dominant. It has good reproducibility with large excess heat. This one is a mixture of this kind of surface orientation. It has poor reproducibility with less excess heat. So 100 is good for the big N number. Hint 3 is from cold-deposited films in LEC. Are they all 100 surface? They were produced based on same instructions. According to electrochemistry for cold deposition, if you are using low current density FCC substrate, halogen ions as additives, you are more likely to produce palladium film FCC 100 surface. So Dr. Golden, Whitehouse, and Biberian were producing palladium film FCC 100 surface. De Stefano were using ion film. It's body-centered cubic material. Ion film was found magnetized. According to solid-state physics, the spontaneous magnetized surface is 100 surface. So, low-energy electron diffraction theory says FCC is the best. BCC is second to best for big N in the coherent jump. So, this explains the good reproducibility in LEC. Imagination. Are there nuclear origin for 5 peaks in electron screening potential? Professor Kasagi pointed out that the peak values for the electron screening potential are too large. We need additional mechanism to explain it. Professor Devinego discovered that this 5-peak pattern is very similar to that in the nuclear transmutation experiment for metal hydride. This similarity is a hint for this nuclear origin. When we measure the electron screening potential, we detect the number of the protons. If the number is greater than expected, there must be an additional mechanism to provide these additional protons. When the deuteron is slowing down, it may have resonance with the screening material. Then they will approach each other, and the deuteron will feed a neutron to this screening material and provide this additional protons. However, this resonant mechanism depends on the atomic mass number, the A number, not the Z number, the charge number. Professor Kasagi's plot was given in Z number. By fortune, the first three peaks has only one stable isotope in nature. So from their Z number, we may find their A number immediately and put them in the cubic root law plot. This is cubic root of A number. This is positive integer number. The first three peaks are on a straight line very well. We may extend them to the fourth peak. That's palladium. This is a good agreement with Kasagi's fourth peak palladium. It provides a chance to verify its nuclear origin because there are 6 stable isotopes in nature for palladium. The palladium 110 is only 12% of it. We may use enriched palladium 110 isotope as the screening material. It should produce much more protons to verify this nuclear origin. However, this enriched isotope is expensive. We may still use natural palladium as screening material and try to detect its products. 58 years ago, palladium 110 enriched isotope was available to produce the palladium 111 ground state and isomeric state. Both of them are unstable. They are beta and gamma radiation. These radiations are unique for palladium 111. So we may measure the beta and gamma radiation in this experiment to verify its nuclear origin. We may use Iwamura's early device to verify this nuclear origin also. When the deuterium gas is passing through a palladium thin film with 100 surface, if the flux peak appear near 147 degrees C, keep this temperature for 16 hours, then measure the beta and gamma radiation immediately after the experiment. It may verify its nuclear origin as well. Summary. 23 years ago, Martin Freshman gave a talk. The title is Searching for the Consequence of Many-Body Effects in Condensed Phase System. He said, hydrogen and deuterium in the palladium lattice could be part of an extended quantum system. So it's a many-body quantum transition. If we are able to detect the beta and gamma radiation, they must be coherent many-body jump, because at such low energy, we can produce this high spin with different parity state. They must be coherent. This is lattice-enhanced nuclear reaction. It shows a bright future for a clean planet.
Xingzhong, thank you very much. We have maybe time for one or two questions maximum. Is there any question? I think people are ready for coffee. That's a problem. So anyway, my friend, I thank you so much for your talk, and we are going to continue our conference now. Thank you very much, Xingzhong Li. Bye-bye.